Hi, good day to everyone. My name is Roberto Cárdenas, and I'm going to talk about the sustainability on biocomposites of PLA and cellulose, biodegradability, energy efficiency, and economic analysis. This work has been realized in the Instituto Politécnico Nacional. First, as an introduction, we know that the reduction of pollution associated to the plastic industry considered three main axes: the migration of fossil materials into biopolymers from renewable resources, the energy efficiency and use of renewable energy, and the final disposition of the plastic products. Each one represents its problems and limitations. For example, high amounts of biopolymers to replace the conventional plastics, or the lack of studies about the specific energy consumption during the production process. In this sense, we propose a composite of PLA and cellulose extracted from pine sawdust, and then different formulations of PLA, cellulose, and maleic anhydride were prepared via reactive extrusion in a twin screwdriver. The study of extraction of the cellulose from the pine sawdust is a previous work and is not presented here. Then, in the methodology, we first studied the biodegradability according to the ISO, determination of the ultimate aerobic biodegradability of plastic materials under controlled composite conditions, method by analysis of evolved carbon dioxide. So we could see in figure 1 the biodegradation system for the carbon dioxide evolution, in the top and in the bottom the biological reactors. Also, we study the energy consumption by monitoring using a triphasic energy meter that allows real-time monitoring of voltage, energy demand, and other relevant variables. The total specific energy consumption includes the consumption of the motor, the herring barrel, the cooling system, and the control panel, and was calculated with the formula. Finally, the economic analysis considers the pretreatment to extract the cellulose biopolymer from the pine sawdust without considering the cost for transportation and recollection, until the formulation with the PLA in order to generate the composite by extrusive reaction. Also, the costs are considered for a laboratory scale process. So, in the parts in the results in figure 2, we have a closer look at the final days of biodegradation, where a difference could be observed. We could see that all the composites biodegrade more than the control, but also that if we increase the amount of cellulose in the composite formulation, the biodegradability also increases. This study was stopped at day 45, but the composites with more cellulose don't seem to be in the plateau phase yet, so we could expect higher rates of biodegradation. Then, the figure 3 shows the energy demand during a work cycle of the twin screwdriver. A, C, and E shows the currents at each line with respect to the neutral, and B, D, and F shows the measured active power of each line. In the first row is for LDPE as a conventional plastic, the second row is for PLA, and the last row is for different composites. For low-density polyethylene and PLA, the energy demand seems to be constant once the effective work is reached. But for the composites, we have a limitation of raw material because the extracted cellulose. So the operation conditions for the composites are not the better for a twin screwdriver. This could be observed in Table 1, specifically in the shear factor. For polyethylene, it's about 90%, but for PLA and composites that are measured with the same operation conditions, the shear factor is low for an extrusion process. Nevertheless, when the specific energy consumption was calculated, it was verified that biopolymers have lower sales than conventional plastics, and that even with not optimized operation conditions, the composite of PLA and cellulose could reduce the impact by reducing the energy consumption during industrial processing. Finally, the economic analysis of the trim processing to extract cellulose, it was more than 2,500 pesos per kilogram, considering the laboratory scale process. And then the final composite have a cost of 136 pesos per kilogram. Considering that the price of PLA is 100 pesos per kilogram, we have a cost increase in the composites. However, this could be reduced by increased the scale process. This economic analysis don't consider the savings from the pine sawdust disposal. So, in conclusion, we know that the monitoring results of biodegradation systems suggest that increasing the cellulose content increase the biodegradation capacity, which is reflected with an increase of the production of the carbon dioxide. On the contrary, the specific energy consumption of the extrusion process on the composites increased with respect to PLA, but the ideal formulation is still lower than conventional plastics, emphasizing that the operation conditions of the extruder were deficient due to the limitation with the raw material. And the cost per kilogram of the composites also could be reduced, particularly by scaling the process, because a great part of the cost is the extraction of cellulose processing at laboratory scaling. So this is all for my part, and if you have a question, please roll it here in the WOBA app, and I'm going to answer so much I can. So thank you for your attention.